Hello, everybody. So, this week's topic, soil, water, and climate relations. So one thing we really think about when we think about soil is that soil has the ability to grow plants and is the medium in which plants grow. And in order to do that, one of the most important parts of that is going to be the soil's ability to store water and then supply it to the plants. Because without soil being able to hold water or supply it to the plants, it's not going to allow for that growth within it. And that's the basic function of soil. So the idea of how can soil store water and how can it supply it to the plants is absolutely critical. So let's take a field scale view of this whole thing and really kind of get down to the nitty gritty and see if we can figure it out. So let's start with some terminology. So surface tension is the property of the surface of a liquid that allows it to resist an external force due to the cohesive nature of its molecules. Well, what does that mean? Well, let's kind of break down some of the ideas. So let's start with the idea of cohesion. So the water molecules are attracted to each other. They want to be near each other and they want to bind onto each other. And that's the idea of cohesion. What's also interesting about water is you have adhesion, which is the attraction of water molecules to a solid surface. So not only do water molecules want to bind on to each other, but they also want to bind on to solid surfaces. And so what we find out with surface tension is that water beads up when it's placed on a flat surface, while most other liquids will just kind of flatten and spread out. Water actually beads up in little spheres and on a flat surface. And so when we get to this idea of surface tension, it's the idea that the property of the surface allows it to resist an external force due to the cohesive nature of its molecules. So the idea that the water molecules want to bind together helps it resist whatever forces are put upon that surface. So what does that kind of look like? Well, let's look at these insects right here, and we see them. What they're doing is actually they're walking on water. Well, how is that possible? It's through the forces of cohesion and adhesion. Because as the insects walk on the water, they're depressing the water surface, but they do not sink. So that surface tension is enough to resist the force that's being put on them. And if we need a little bit more explanation, you can click on this YouTube video right here in the bottom right corner by pausing this video and then going into your lecture notes and clicking. Go ahead and do that now. So soil water retention. So the water molecules are attracted to the surface of soil particles. That's the idea of adhesion. So so we've got water. The water just wants to hang on and be around water because wants to be around soil because water just always wants to be around something. And so it being in the soil, it wants to hang out around the soil. And this is where surface area becomes important because we know that clay has a huge amount of surface area as opposed to sand, which has much less surface area. So there's much more energy required to remove water from clay than sand because there's so much surface area, which means there's so much water binding on to all of that surface area, which means clay is going to hold water way more than sand just because of that idea of the larger amount of surface area. Water molecules on the soil surface are going to be held very tightly. So if you imagine a piece of soil, the water molecules that are right on that piece of soil are held extremely tightly to it. The water molecules in the area near the surface of the particles are going to be held less tightly. And then water in our micropores is going to be held loosely, and water in our macropores is going to be held the most loosely. So in terms of the idea of us holding water, going back to these ideas of adhesion and surface tension, when it's right next to the surface tension is great. When it's far away from the surfaces, you're going to have not any or not really good surface tension at all, and that water's going to move much more freely. And so when we use the term matrix potential, that is the energy required to to remove water from the soil. So if we want to take water away from the soil, that's the matrix potential. Water is going to be first lost from the large pores, farthest away from the surface, then the small pores, next from the near particle surfaces, and then lastly from the particle surfaces. And water moves out of the large pores mainly through gravity. So at this point, let's talk about the three different ways soil water can be classified. And that's going to be through gravitational water, capillary water, and hygroscopic water. And if you say to yourself, well, like, what does that mean? Or what's the differences? Let's talk about it, because what we just described in the slide before, we've already talked about the actual differences between these three. So let's start with gravitational water. So gravitational water is water held loosely in the largest pores and drains out first by gravity. So another way to say that is water that drains freely from the soil from 0 to 3 days after irrigation. That's kind of the fancier way to say it, but really it's water held loosely in the largest pores that's going to drain out first by gravity. And if we look here on the left, this is what we're talking about. So gravitational water, it's just going to drain right through. So then what about the next one? So we mentioned this idea of the water near soil particles. So that's going to be capillary water. And capillary water is going to be the water in the micropores and near the surface of the soil particles, but not on it. And so capillary water is water that remains in the soil after gravitational water is drained out, that is subject to the laws of capillary movement, and that is in the form of a film around the soil grains. So it's not on it, but it's near it, and you can see here in the background kind of forms this film that is near all the soil particles. So after the gravitational water gets pulled out of the soil, the next to go would be the capillary water. And then we have water on the soil particles that are right on the surface of the soil particles. That's hygroscopic water. And that's water that's held so strongly by the soil particles through adhesion, because we know water wants to stick to the surfaces of things. And that water is not going to be available to plants because it's held so tightly onto the pieces of soil that it takes so much energy that plants are like, forget that. It takes way too much energy. Not gonna even spend my time trying to get that stuff. So let's take a look at it again with this idea of all three of the waters. So here's just the idea of hygroscopic water. So see that this black outline around the soil particle, that's going to be our hygroscopic water. Our capillary water is this water that forms this film around the soil particle, and then our gravitational water is all this just water hanging out. So if we hit wilting point, which we're about to talk about, we have some soil particles that don't have even hygroscopic water on them anymore, and we have some that all they have is hygroscopic water. If we have, this is going to be our available water. We're about to talk about that. We have some water available. So we've got some capillary water available. If we reach field capacity, also about to talk about this, and saturation, then we have a bunch of available water. But now here's where it gets tricky, because we need the soil to be healthy just as much as we need it to provide water to the plants. And one thing that we know doesn't make soil healthy is if we have water taking up all the pore space, because we need our best soil has that balance of 50% water and 50% air in that pore space. So if we get to saturation, or we get to saturation for too long, we don't have enough air in the pore space, and we can actually hurt plants just as much through saturation as we can in having no water. So let's talk about these terms that I just threw at you. So field capacity. Field capacity is the amount of water, usually in for us over here in inches per foot of soil, held by the soil after the gravitational water has drained off. So it's the amount of soil moisture or water content held in the soil after excess water has drained away or percolated through the soil, and the rate of downward movement has decreased. Usually you reach field capacity 2 to 3 days after rain or irrigation. And you can see right here in this chart the idea of here's our water content, and just right when it's happening, of course, tons of water. But then as we get a couple, 2 to 3 days out, then we've hit our field capacity. And when we say field capacity, it's the amount of water held in the soil after all the excess water, or really that gravitational water, or the water held most loosely in the large macropores, has drained off. Permanent wilting point, which was on the other end of the spectrum from field capacity, that's the amount of water held in soil when plants are permanently damaged from water stress. So permanent wilting point, or just wilting point, is defined as the minimal point of soil moisture the plant requires not to wilt. So you need to have at least this much soil moisture. Otherwise, if you get past this, the plant is not coming back. No matter if you finally started to water it, then it doesn't matter. It hit that point, and beyond that, it's going to die no matter what you do. If moisture decreases to this point or any point lower, a plant will wilt and can no longer recover its turgidity. The idea that it can hold itself up and be strong when placed in a saturated atmosphere for 12 hours. So let's take another look at all those kind of ideas that I threw at you. So we said saturation. Saturation's the idea that we'd be all the way past field capacity. We have as much water as we could possibly deal with. In fact, we have too much water. We got excess water. And we know it's excess water, and we call it excess water because we know that we need air in those pores just as much as we need water. And we know that the best version of that is 50% air and 50% water. But if all the pore space is taken up by water, that's not great. So the soil has a process in it where the first things that are going to empty out are those large macropores, and so that water drains out easily through gravity, and that also helps us get water through the different horizons of our soil, and then eventually into our aquifers where we store groundwater. So the soil has all of this process kind of worked out because we got to save that water. We got to use that water. We can't just waste it. We've got to have it go somewhere. And so then eventually we get to the point of field capacity, usually about 2 to 3 days after the saturation from either a precipitation event or irrigation. And so in between field capacity and permanent wilting point, we have this idea of available water. So the idea that this is when we have water available for the plant, and it can get water and use water, and it's right there. It's available. Come and take it. Come get all the nutrients that you need. Perfect. But if we keep using water and we don't get more water, we don't get any recharge or anything else, we'll eventually get to wilting point, and then we get permanent wilting point where we've hit that point where no matter what we do, that plant is going to die. And so we don't want to really hit permanent wilting point, especially if we're out there growing crops. So I think another way we can kind of look at it is this idea. So saturation, gravitational water draining, we're kind of good with that idea. But then it's really this more of idea that we really want to keep going in this area. We want to maintain water in this range for optimum plant growth. We do not want to get over here because there's just a point where we're going to get too close, and then eventually the plant's not going to come back. And remember, so even at saturation, the plant's going to wilt because there's too much water, there's not enough air. We need both air and water. Here, we've got a healthy plant, but we're just wasting water because there's too much water in there. Here we've got a healthy plant and no water is wasted. That's where we're at our field capacity. But then over here, the plant's going to wilt because there's not enough water, and then eventually we get to that permanent wilting point where it's not going to come back. And so we talked about the idea of available water. And so available water capacity is the amount of water held in the soil between field capacity and permanent wilting point. It's the maximum amount of available water that a soil can provide to a plant. And available water capacity is an indicator of a soil's ability to retain water and make it sufficiently available for plant use. If a soil is in this moisture range, the soil is said to be friable, which is the idea that it's easily crumbled with your fingers. And I think if you look at this soil in this picture, and you think about if you were to pick that soil up, and you can see it's kind of wet, and you were to just pick it up and kind of just move it in your fingers, you'd see that it just would kind of fall apart. It'd be friable. So what factors are going to determine the amount of soil moisture that we have? So what's going to be happening that's going to tell us whether we have soil moisture and how much soil moisture we have? The amount of snow, rain, and irrigation, so the amount of precipitation or irrigation that we have, the rate at which the soil permits water entry, and we'll talk about that later in the lecture. Your water storage capacity of the soil, we're also going to talk about that later in this lecture. Your evaporation rate, also coming up. The height of your water table. So your water table is the point at which, when you dig into the ground, the first point that you hit water as you dig down, that is going to be your water table. So how high or how low or how much, how far into the ground is your water? That's going to determine the amount of your soil moisture, right? How wet is your soil versus how dry is your soil? The rate at which water can move within the soil, that's percolation, and the amount and type of vegetation as well. Those are also going to determine the amount of soil moisture. So how can we increase the amount of available water to a plant? So how can we increase this amount of available water? So first, precipitation. So better utilize snow and rain by keeping water on the soil surface. You can do this through windbreaks, keeping snow in place with some cover. You can do strip cropping, contour strips, grassland farming. You can leave crop residues that can absorb water. There's all sorts of different ways that you can do it, but you want to keep as much precipitation as you can. Some other things that you can do: drip irrigation, making sure that water, if we're going to use irrigation, that our water is being used efficiently and goes where it needs to. We can focus on the water entry, so we can reduce cultivation. We can use green manures. If it's alkaline soils, we can try and correct them to make sure that the water is actually getting into the soil the way it needs to. We can work on the storage capacity, so increase water retention. You can do that with manures. You can do it with straw or mulch. And you can do it through tilling of the soil after harvest. And then also evaporation. So we can work on evaporation through things like conservation tillage and strip cropping, and also the idea of any sort of organic mulch, any straw or wood chips or any of that sort of thing. That's going to keep some of the evaporation from happening. So how does soil water actually get used by the plants? So the easiest way to think about plants is that plants are on a liquid diet. And so they're going to absorb most of their nutrients from the soil solution. So if we look right here on the right here, we got our plant root, and we got a soil solution fraction where we got our ions, just these little positively charged ions just floating around in the water, in the soil solution, and they're freely available to be taken up through cation exchange with the plant root. Another way to look at it, here's our plant root. It's just sticking out there. We've got our soil particles. We've got our air in our macro or micropores. We got our water in our macro and micropores, and our water is going to just get there to the plant, and the plant's going to just take it in. The plant roots take up water from both the large and the small pores, the macro and the micropores, but they lack the energy to remove water tightly held on surfaces. So we talked about that idea of the hygroscopic water. That's that water that's really stuck through that idea of surface tension and adhesion to the soil surface, and the roots aren't going to spend that sort of energy to go and take that water. They're just going to focus on the water in the macro and the micropores. So in terms of soil water management, so how are we going to manage water, or what things are we focusing on? So the aim of soil water management is going to be to provide sufficient water required by crop plants for optimum growth without endangering the health of the plant through a lack. So without endangering the health of the plant through a lack of soil air. And it's really important, this idea, because I've kind of mentioned it before, that our best soil is 50% air and 50% water in those macro and micro pores. And so we want to provide sufficient water, but we don't want to provide enough water that there's not enough air in the soil. So that's our goal. And so another thing that becomes interesting with trying to manage the water in the soil is the idea that when we need water most, that's actually not when we get water the most. And so, especially out here in the western United States, we have a wet season and a dry season. And the main growth period of our crops is way closer to the dry season than it is to the wet season. And it's actually kind of that transition area between it. And so moisture needs during the main growth period usually are in excess of the amount of rainfall at that time for most places. And so therefore the soil must act as storage and carry water from the dormant season or the wet period through the growing period. And so two things that you need to make this happen are infiltration and water holding capacity. So let's talk about those two things. So in terms of infiltration, all we're really talking about is the process by which water enters the soil pore spaces and becomes soil water. So the idea that the water actually starts off in the water cycle, we get precipitation, and then that precipitation finally gets itself into the soil. That's through the process of infiltration. And if we look here at this version of the soil texture triangle that's classified by infiltration rate, we can see that clays have a very, very slow infiltration rate. We can see that sand has a very, very high infiltration rate, and we can see that silt is kind of in the middle, which we've kind of talked about those ideas before, but just trying to put that the idea of texture and infiltration together, because texture is super important, and it really comes back down to just those basic ideas of surface tension and adhesion, because clay, with its high amount of surface area, is going to hold on to water much more. So in terms of the texture differences when it comes to available water and field capacity, clay soils are going to have the highest field capacity, but they're going to have the lowest available water capacity, because water is held tightly to those particles and it's just stuck to that surface. And because there's so much surface in clay that they're going to hold water well, but the water's not going to really be available to plants. Sandy soils are going to have low field capacities because they don't hold water well, but they may have moderate available water holding capacity, because all the water that is left after drainage is going to be available water to the plants. Loamy soils, which are right in the center of our soil texture triangle, are going to have a high field capacity and a high available water capacity, and that's why they're the best of the best in terms of our soil textures. The different pore sizes are going to hold water better. Your changes in textures in soil profile are going to hold water differently in different horizons, right? Because we say clay soils or sandy soils, but all soils have combinations of these, and within a soil profile and the different horizons, they're not always going to be the same as you go down the profile, right? You might have sandier soils on top and then more clay soils as you go down in the horizon, which we know is kind of typical. And so because of that, you're going to have changes in texture, so you're going to have changes in the water holding capacity of the different horizons. And then if you have, or your organic matter content of your soil then is going to be super important as well, because we know organic matter has a high water holding capacity. So the more organic matter you have in your soils, like a prairie grassland soil, the more water holding capacity you're going to have, and the better your soil is going to be. So then let's talk about the idea of percolation, because we talked about the idea of infiltration, of how the water gets into the soil, but then what happens when the water's in the soil. So then that's the idea of percolation. So that's water moving downward through the soil profile. And so you can have both saturated and unsaturated flow involved. We talked about the idea of when water is saturated, and then unsaturated is when it's not saturated. Your rate of percolation is going to be relative to the soil's hydraulic conductivity. And what the soil's hydraulic conductivity is the ease of movement of water through the soil. So how fast water can move through the soil is going to depend on your hydraulic conductivity, which is how well does your soil allow for water to move through it. And so if we kind of just look at this diagram here, we've got infiltration, gets the water in there, but then how the soil moves it through or holds onto it, or basically going back to how we started, whether the water is binding on tightly to the water, or whether the water is binding on tightly to the soil, or whether it's just kind of loosely hanging out. If it's loosely hanging out and there's a lot of that, like in a sandy soil, water's going to move through and percolate down really easily. If it's a heavy clay soil where you got lots of surface area, which creates lots of surface tension, which has lots of adhesion, takes way more energy for that water to then move downward through the soil, you're not going to have a higher rate of percolation in those clay soils. And so then that gets us to kind of an overall idea of the soil-water balance. And that's really going to be based on three factors. So how much precipitation you have, or how much water you have coming in to the system, your potential evapotranspiration, and evapotranspiration is just the combination of evaporation and transpiration. So the idea of water basically leaving the system. And then our available water holding capacity. So what types of soils do we have? What textures of soils do we have? And what is our capability to hold on to the water? Because if we basically think about it, the water balance is the idea of the water coming into the system and the water going out of the system, and then just the water holding capacity is, okay, so if we know how much water is coming in and how much water is going out, then we know how much water is in the soil, and then how much of that water is going to be held by the soil so that it can be used up and taken up by the plants, and how much of it's just going to flow through and become groundwater. And so those are our three basic factors for our water balance in our soil. And then in terms of soil water processes, we can break it down into four ideas. The idea of utilization, of deficit, of recharge, and of surplus. And your book goes into this bucket analogy, which I think works out pretty well. So if you start off with the idea of the beginning of the growing season, our plants need to utilize the water. So this is where our evaporation is going to be greater than our precipitation, which is what we mentioned before. And because we don't really get water at the exact time that we need it. Water needs to be held by the soil, held in storage until this point, because now this is when we're going to use it, because now the crops want to grow. Now the crops are thirsty. Now they're on that liquid diet. They're waking up from dormancy and they're like, feed me, I need to eat. And so your bucket, if we go with this bucket analogy, your bucket's going to start to empty at this point. Eventually, as you get through the growing season, and hopefully you get really close to the end of the growing season before this happens, but sometimes you don't, you get to deficit, which is all your available water holding capacity is used. Your plants could have used more, but you no longer have any water available. You're running a deficit at this point, or basically your bucket has run empty. So now after the growing season and we get back into that dormant rainy season, we get hopefully we get some recharge, which is now during the dormant or wet period, our precipitation is going to be greater than our potential evapotranspiration. So now the idea is our bucket's getting refilled so we can start this whole cycle again. If we get too much water, we're going to have a surplus, which is basically thinking of the idea of the bucket overflows. And that's where you see surface runoff, you see problems with erosion, and we basically, you almost look at it like water's getting wasted as opposed to getting used into the soil. But that's also how we end up with things like lakes and reservoirs, is where we know that not all the water is going to be able to make it into the soil, so we got to figure out these other ways to keep that water and not just let it disappear, because we know how important water is to us and to the plants and to the whole planet. And so let's kind of just take the simplest look at that. So we know in terms of our factors in water balance, we know precipitation is water into the system. We know potential evapotranspiration is water out of the system. We want our bucket to be filled to the point where water fills our pore spaces, but we want to make sure that we don't fill it too much, because we know we want soil air to be in there as well. And if it gets filled too much, that also leads to the problems of having that surplus and having that surface runoff and having erosion and not having water not make it into the soil, which we know we don't really want that to happen too much. We want to make sure that our soil gets all the water it needs, because when it has water, it can grow plants and it can store water, and it also then fills up aquifers that hold the water that then we use as groundwater, that we use to then irrigate crops or to use for drinking and for all of our purposes. And that is how soil uses water. And that, to me, is just an amazing process.